Particle detectors do not usually offer spectacular images or obvious signs of historical discoveries. Sometimes everything is reduced to an almost imperceptible trail left by a particle that has traveled millions of years before disappearing. This changed when a neutrino telescope in the Mediterranean Sea recorded a signal with an energy never seen before. If you like this content, don't forget to subscribe and give like. Your support is essential to keep creating more videos on science and discoveries. Let's go deeper into this fascinating find. The event, known as KM3 23023A, not only broke records, but also posed an uncomfortable question about its origin. The explanation proposed in a recent study goes far beyond the usual astrophysical sources, suggesting that this extreme particle could be the footprint of an explosion of a primordial black hole. The work, signed by a team of researchers, proposes that if this interpretation is correct, we would be faced with a possible confirmation of Hawking's radiation, a theoretical prediction that has remained unverified for half a century. This opens a new field of study in particle physics. The neutrino detected by KM3 NeT reached an energy of the order of 100 to 200 peta-electronvolts, far above what the known sources of the cosmos produce. The finding is exceptional and generates tension between the experiments of KM3 NeT and IceCube, which have not detected comparable events. The scientific article points out that there are no known astrophysical sources capable of producing these extreme signals. Supernova explosions or gamma-ray bursts are not enough to explain the energy and frequency of these events, which poses a challenge for scientists. The primordial black holes are objects that have not yet been directly observed, but could have emerged in the first moments after the Big Bang. Their possible relationship with dark matter makes them attractive candidates for understanding the early universe. The new work not only rescues the idea of primordial black holes, but also proposes a mechanism for some of these black holes to survive for billions of years and explode today. This is connected with Hawking's radiation and its final evaporation. Hawking's radiation shows that black holes are not completely black and can emit radiation. This process is virtually irrelevant to black holes of stellar mass. But the primordial black holes could be in the final stages of that process, culminating in energy explosions. The proposal to include a dark load in the primordial black hole model makes it possible to reconcile the observations of KM3 NeT and IceCube. This approach suggests that the emission of neutrinos varies depending on the load, which helps explain the discrepancy between the two experiments. The neutrinos are cosmic messengers that interact weakly with matter, allowing them to travel long distances. The study details how these neutrinos are generated during explosions of primordial black holes and how they are detected on Earth. The study proposes a framework that can be refuted or reinforced with future data. If coincident events in neutrinos and gamma rays are detected, the hypothesis could gain strength and offer the first observational evidence of the evaporation of a black hole, as Hawking described it.